I'm Everett Hildenbrandt, the CTO runtime verification, and I'm going to be talking about Firefly today. I talked a little bit about Firefly yesterday in kind of a quick teaser 30-minute main stage talk. I'm going to quickly go over what I covered in that talk first, and then I'll go a little more in depth about how to use Firefly to improve your test suite with some demos and some live interaction. I'll be demoing some features that aren't released in Firefly yet. They will be released shortly within the next week. And then I'll also be teasing some features that won't be released for another month or two towards the end. Okay. So Firefly, Smart Contract Quality Assurance. Just real briefly, this is the overview of the presentation. I'll talk a little bit about what is Smart Contract Quality Assurance and how Firefly fits into that. And then talk a little bit about basic usage of Firefly, as well as some of the planned features. So right now, Firefly is version 0.1.0, and within the next week, we're going to be releasing version 0.2.0, which will include this I'll show today. So this can be used as kind of a primer or a tutorial on how to use that feature. And then version 0.3.0 is not going to be out for a while, probably another month at least. And then I'll talk a little bit about another tool that is somewhat tied into the Firefly tool suite, which is this ERC20 verification tool. And I can take questions at the end. Okay. So first, just broad overview, what is software quality assurance? These are processes we put in place to ensure code quality, which is important in the context of blockchain. There's two broad categories for this. There's absence of bugs in the code, so that would be tools that find bugs for you or fix bugs for you, or processes that find the bugs, so code review, stuff like that. And also, does the code architecture actually perform the intended function? So you have some high-level idea of what you want your code to do, like, implements a consensus protocol or implements a stable coin or something like that. And you want to know, does the smart contract I implemented actually achieve that effort? Broadly, it's broken into two different categories. One would be one-time techniques, and then there's continuous techniques. The one-time techniques are usually manual or human efforts. This will include things like audit and code review. Sometimes formal verification falls into these one-time techniques or formal modeling. And then there's continuous techniques, which a lot of people will integrate into their continuous integration pipeline so that it's run on every single change to the code. So this will include things like code review, which is actually a human effort or a manual effort, but usually a lot of companies will include a code review portion to their pull requests. Testing, which has a lot of different types. There's unit testing, which most everyone's familiar with. But there's also things like property testing and random testing, end-to-end tests, integration testing. There's tons and tons of different tests. So in the world of Ethereum, what that might look like is, a unit test might just test that a single function behaves as expected given certain inputs, and an end-to-end test might look like setting up an actual mock network and running some transactions and seeing what the post state looks like after all those transactions run. There's static and dynamic analysis tools, which here you can think of things like linters and linters, things that check for memory leaks, stuff like this, things that are just checking the code without actually looking at your test suite. So they just kind of look for common code failure patterns. And then kind of at the harder end of the spectrum is mechanized verification or model checking. So if you have a modeling technique or a theorem proving technique that is mechanizable, so think like the tool Coq or Isabel or K, which is the tool that we develop, then you can integrate that into your continuous integration, and it will make sure that the verification carries forward throughout the code. So mechanized verification and model checking is largely where we runtime verification have worked in the past. But Firefly is our attempt to kind of bring more tools in the testing world to users so that they can improve their own quality, their own code quality without having to contract us to do so. Okay, so just a quick overview. Why are we applying quality assurance to smart contracts? It's actually the perfect place to apply heavyweight quality assurance techniques because the code is immutable, so bugs are hard to fix. The code handles money, so bugs are expensive, and the code is small. So there's a lot of heavyweight quality assurance techniques that wouldn't be feasible in other realms that suddenly are feasible or even commercially viable. You don't even have to apply for like a really expensive government grant or something like that just to verify, a few thousand lines of C code. Here, it's actually feasible for companies to pay for verification just themselves. So in the world of smart contract development, testing is pretty common. So, we're at TruffleCon. So Truffle is an example of a testing framework. Audits are pretty common. So you pay someone with a fresh set of eyes to look over your code with a mind for security, and they try to find bugs in it, bugs at the code level usually, and then also sometimes they'll look at bugs at the overall design level. And then formal verification and formal modeling happen, but they're not super common because they're still pretty pricey. So this will be really sensitive applications. A couple of our former contracts have been, with the Ethereum Foundation, with the deposit contract, for example, or other big contracts that kind of underpin the basis of what a lot of other DeFi or dApp applications build on top of, where you really want to make sure that everything is going to go right. So that's kind of the landscape. So yeah, coming back to the motivation for Firefly. So there's a lot of developers that approach us for verification or audit tasks, but they'll balk at the price or the time that it takes. And there's not much we can do about the price or the time it takes because verification is hard. Full form of verification is difficult, and it takes a while to kind of get all the steps right. But there's a lot of times that there's smaller steps that developers can take that they haven't taken to improve the quality of their code without having to approach us for full formal verification. So Firefly kind of aims to help developers before that audit or verification stage. Kind of the goals of Firefly, it's going to be free to use. It integrates with Truffle, so kind of one of the more widespread testing platforms. We do have experimental integration with some other testing platforms as well, but Truffle is by far the kind of easiest one for us to integrate with. And we want to leverage as much as possible the existing test suite and testing tools of the developers so that we're not having them learn some new tool or some new language or something like that. So the overall idea here is that, setting up Firefly is a one-time setup similar to setting up Truffle or something like that. So you just set that up early in your code development cycle and testing cycle. So that length of time doesn't change very much. But then by the time you get to the audit cycle, you have a little higher confidence in your code and it's a little higher quality. So maybe the audit takes less time. So that's the long-term goal of the Firefly project, is to make it so that the audit at the end before you launch is a little cheaper and a little quicker. Okay. Just brief overview of using Firefly. We're integrating directly to Truffle, as I said, and we have experimental support for some other tools. We are a drop-in replacement for Ganache CLI. So instead of calling Ganache CLI, you call Firefly Launch. And we support many of the same common command line arguments that we've seen in the wild. We probably don't support them all, but if you see one we don't support and you message us, we'll see about supporting it. And we're running an instrumented version of KVM. So K is a formal semantics of the Ethereum virtual machine. It's a formal specification of the Ethereum virtual machine that can be used for both execution and for formal verification and model checking, and we instrument it to collect a bunch of extra information about your tests as your tests are running, so that you don't have to add any extra tests. We just collect extra information about how those tests are running. KVM is tested very thoroughly. We tested against the exact same conformance test suite that all of the other clients, all the other major clients like Geth and Parity run. and we pass all those tests. We support all the hard forks. We support, setting things like chain IDs and stuff like that. What Firefly brings to KVM is the ability to run as a full node, basically. So you can run Firefly as a full node on the blockchain, and have it process transactions and stuff like that. And we have pretty good performance. Our performance is better than Ethereum JS VM, which is what Ganache CLI is using under the hood. And it's a little better than the Python one, which I'm forgetting the name. I think it's like PyEVM or something like that. We're just slightly better than that. We're not as good as like Geth or Parity, which have, they're native. They're not compiled from a formal semantics, so they can make a lot of optimizations we can't make. Okay, so enough about KVM. So to run your tests using Firefly, basically all the Truffle commands you would normally call, you call Firefly instead, and it's just a real thin wrapper around Truffle, because there's a little extra bookkeeping we have to do to kind of collect build artifacts and stuff like that. So, oh, you're good. So we just have this Firefly command, this real thin wrapper around Truffle. You can look at the code, and it's not very complicated. And then we generate a report which displays extra information about the tests. And currently that extra information that we display is bytecode level coverage, which differs from a lot of coverage tools. A lot of coverage tools give you basically solidity level coverage. We collect coverage at the bytecode level for the purpose of not mangling the behavior of your tests or the gas usage of your tests. We don't do the solidity instrumentation technique that a lot of testing does. Okay, so that's basically a review of what I went over yesterday for anyone who missed it, and kind of keep the presentation all self-contained. And so now I'm going to jump into the demo. And so for this, I'm going to have to switch between the screen share between different screens, unfortunately, but that's just what we're going to have to do. Okay. Sorry, 1 second. Okay. Okay, so this is the Firefly website. I'm actually on the sandbox version of the website, which is for the runtime verification developers. You would use just the normal Firefly website. The sandbox is usually just a couple commits ahead of the production version, which is just without sandbox. But it's not as stable, so I would just stick with the production one. This is the page that you're dropped into when you look at the Firefly website. And so you can look at kind of what the final result will be by clicking this interactive report and this kind of little diagram here that explains what the output is telling you. And there's a little helpful hint dialog that will pop up and tell you how to view the report and how to do various things with it. So that's how you can explore the sample report. We include the output from Truffle, which shouldn't be surprising to anyone. It's just the same. It's just the same output that Truffle gives. So that's kind of, shouldn't be too surprising. And then we also include a coverage report, and the coverage report is going to be at the bytecode level, like I said. So let me open up an example here, and you can make it full screen to make it a little bit easier to read. Let me zoom out a bit. So here's our ERC20 extension contract. The contract here that's being run is this one at github.com/runtimeverification/Firefly demo. It's just a real simple ERC20 and some extension. It's a no-brainer contract. Didn't do anything fancy with it. There's tons of security holes in it. So don't use this contract for anything live. It's just a real basic ERC20. And then we have ERC20 Ext, which adds a few methods just to show what inheritance and stuff like that looks like when you're working with this tool. So the ERC20 Ext contract, we can see here, okay, the mint function is not tested at all, and if you click on a given line in the in the solidity report, it'll show you, hey, these are the byte codes associated with that given line. They'll show you, okay, so these are associated with some other function here, but this is actually the meat of the mint function itself, and there's no tests for it. Okay, so that's not good. Burn function similarly not tested. Display name function is tested, so we can click on this line here, 26, and we can see, okay, every opcode associated with line 26 is tested. So let's step into the contracts that this one inherits from, which is ERC20 and owned. So if we step into ERC20.sol, we can see that we have a little bit more variety here. So there's the red ones, which are untested, so the symbol function is not tested. There's the green ones, which are fully tested, meaning every opcode associated with that line is tested. So this is the symbol function, it's untested. And then there's yellow lines occasionally, which show that, you know, that line was hit, that solidity line was hit, but not every opcode associated with that line was hit. So for example, here we can see, okay, we never called the transfer function where the target or the sender was address 0, where the recipient was address 0. So those are two test cases we missed. And it could be that if a piece of code is unreachable, it could be that this is reporting yellow or even red, but actually that code is unreachable. So there's going to be no way to reach that line of code. But in this case, we actually can reach it. Okay, so mint and burn, the internal implementations of these functions are untested. Similarly, approve, we have a couple of requires clauses here that are only partially tested. Now, I'm only showing some requires clauses being untested or fully tested, but actually, we measure more information than just was the opcode visited or not. If it's an opcode that branches, we visit, was the opcode visited and both branches that the opcode could take were taken. So that's the example here with this jump by instruction. Sorry, my computer's lagging a little bit. Give it a second. The jump by instruction says that the jump was skipped for opcode at line 1878. And basically what that's saying is we did visit the jump by instruction and we went straight to the jump test. We didn't step over it and also take the case where the jump by failed, which is what results in this revert case. So anyway, I'm just trying to go in depth and show you guys how to read these coverage reports a little bit. Okay, anything else? Oh, then, so another thing that we do as well is, for example, here, this sub opcode right here. Give that a second. The sub opcode is going to be associated with, I believe, the ABI encoding functionality. But we also, for all arithmetic opcodes, we record, did you visit it and it overflowed, and did you visit it and it didn't overflow? So your tests have to test both the overflow and not overflow case for all arithmetic opcodes as well for us to consider this line to be green. Now that's not always going to be possible. Like this sub opcode here is associated with the ABI encoding and decoding functionality of the Solidity smart contract. So there's no way you're going to be able to write a test that actually visits that sub opcode in both the overflow and not overflow cases. But that's okay. We just want to give the extra information to the user when possible. Okay, so that's the overview of how to read these coverage reports. And now I will jump into showing you how to run the program and actually generate the coverage reports. And I'm going to be using the same example, and we'll kind of interactively build up the coverage as we go, both manually and using the Blackbox tester that I discussed earlier. Okay, so once again, this is a Firefly demo repository. So I'm going to jump right into this start button here. Go ahead and close this one. And the start button takes us to installation instructions. Now, if you're not logged in, I'm already logged in here, so it's giving me the log out option. It's going to ask you to authorize GitHub when you click login. The only thing we're collecting from GitHub is your GitHub identifier. Basically, it's just so that we don't have to store our own database of user identifiers. We can just ask GitHub, hey, who's this user? So that we don't have a potential security breach other than just, you know, using your GitHub identifier. So it's not like we're not trying to get your private repo access or anything like that. We're just using it as an authenticator. And then the installation process, we have actually 3 ways to install. One way is not listed here. One is the Ubuntu package, which you can just hit this and you get a Debian package. That's the technique I use because I just run Ubuntu VMs. And then the other one is a binary user install, which basically you just install all the needed dependencies of the, here we give an example for Ubuntu, but you have to translate this to whatever your distribution is. And then you can curl the install script and pipe it into SH, and that basically just downloads the Firefly binaries and just puts them somewhere on your path. Specifically, by default, it'll put it at your home directory /.local/bin. So you just have to make sure that your path is set up to access those. And then a third way, which I'll get listed on the website this week, is we have Docker Hub images. And these are public, anyone can use them. This is just an Ubuntu Bionic image with Firefly pre-installed. So it's just the most vanilla Ubuntu Bionic image you can have with just the dependencies needed to make Firefly work. And so you can go here and you can either set up your own Docker file that pulls from, using the from directive in Docker, this tag, or you can do like docker run -it and then this tag basically, and then it'll drop you into a Docker container that has Firefly installed. Okay. So if you want to play around with it, this Docker option is great, especially if you're on Mac, because we're not releasing a Mac package yet. It is on our to-do list, but we've had some difficulties doing that. And we also are working on Nix packaging for it, but that's not done as well. Okay, so I already have it installed, so I'm going to jump straight to the run step. Running Firefly, it's the same workflow that you have with Truffle. So you would do, normally you do Truffle compile, Ganache CLI, Truffle test, and then this is new here. This is a Firefly only command, and then this is just to shut down the client. So Firefly compile is just a thin wrapper around Truffle compile, once again, that does a little extra bookkeeping so that we have the extra data we need to generate that coverage report. And then Firefly launch is just the drop-in replacement for Ganache CLI. Firefly test, which is just the thin wrapper around Truffle, does a little extra bookkeeping. And then Firefly coverage actually is what collects and collates the coverage report. And then once you're done with all that, if you want to view the report in browser, you do the Firefly upload command. So I'll get to that in a second. For now, though, I'm going to switch over to showing my terminal to show the workflow. Okay, give it a second to pop up there. There we go. Okay, zoom in once more. Okay, so I'm in this this runtime verification / Firefly demo repository. I'm on a branch that I called add tests, where I just added a couple tests this morning for this demo. But you can just use master if you would like. And I've already done like the npm install. I've already got Firefly installed globally. So we're ready to go straight into the demo without having to wait for that install to happen. The install is really quick, but it just basically moves some binaries into place, but I just didn't want to have to, everything goes wrong during a presentation, so I just set it all up ahead of time. Okay, so first thing to do is look at our Truffle config to see what port we should be running our Firefly on. So port 8145. So I'm just going to say Firefly launch -p 8145. All right. And there it says that the Firefly client is ready. Went through some state initialization stuff, and you can see that it found the Truffle config, so it's using Truffle. If you have like a Biddler config, it'll default to using Biddler instead. But support for Biddler is experimental right now. Truffle is the one we support much more robustly. So then I can do Firefly compile. I already did this before, so it should be a no op, but I'll go ahead and do it again anyway. And this is Truffle's output right here. It's compiling the contracts, and then there's a little extra stuff where we do some bookkeeping, where we grab the JSON artifacts emitted by Sol-C and zip them up. Basically, that's going to be sent to our server for displaying the Solidity code a little bit nicer. Okay, so Firefly compile ran fine, and now we can just run Firefly test, which is once again just a thin wrapper around Truffle test. So it compiled our tests, and it ran our 7 tests. We just have 7 tests. Okay. And so I can look at the test files here. We have a test that the initial mint when you make a new ERC20X called gold works, and that the balance is adjusted correctly. Transfer from works in some capacity. Calling some owner-only function, and then transfer to the 0 address fails using Truffle's Truffle assertion reverts library. Okay, so Firefly succeeded in running the test. So now what I can do is I can say, okay, Firefly, collect the coverage report. And so it's going to collect the coverage report. There's a bunch of things that are collected, basically. And then I've already set up, I'll show you how to do this in a second when I switch back to the other terminal, but I've already set up my Firefly token. So there's my Firefly token. I'll show you how to do that in a second. So I can just call Firefly upload. And Firefly upload is giving me problems. Give me 1 second. Okay, I am going to have to actually show you guys how to set up the Firefly token because I deleted it for the purpose of the demo. Okay, sorry about that. Okay, so the last step here, notice when you do Firefly upload, you have to have a Firefly token set. This token is just stored in an internal database that just associates with your GitHub ID. It's just to make sure that only you can view the reports that you are generating, to keep them private in case you don't want to share your Solidity code. So I'm just going to click this link, and it takes me to a token page here. And this is in my dashboard. So you can also get to it by going to the top bar and going to dashboard and going to tokens. And I'm going to make a new token called TruffleCon. Create that token, and then I can copy this token to the clipboard. Okay. And then over in my terminal, I'm not going to bother switching the screen right now, but I'm just going to say export Firefly token is equal to that token I just created. And then I'm going to run the Firefly upload command again. I'll go back to the instructions. So yeah, I just exported and set the Firefly token, and then I did the Firefly upload. So back in the dashboard now, you hit the next step. You should be able to view your reports. And I have one report now, which is using this TruffleCon token. There's no commit associated with it because I didn't upload it with a commit tag associated with it. The output is exactly what we saw in the terminal before. This is only slightly different than that sample report I showed you because I'm using the same repo, but just with a couple tests added. And then the coverage report is here again. So remember in the sample report, we had 30% coverage on the ERC20X token, and now we have 35% coverage. So huge improvement. It's just because now we're calling this transfer function in some limited capacity. And we're also testing, maybe the recipient is 0. So notice that in the previous report, let me take us there. In the previous report, we, for the ERC20 token, both of these lines were full yellow, meaning that we hadn't exercised the revert clause for either of the lines. But in this report, this one is still full yellow, so we haven't tested the case where the sender of the transaction is the 0 address, which is it's a hard thing to test anyway. It's not a very realistic scenario. But we can test that the recipient is the 0 address. And so I added a test that the recipient is the 0 address in this branch I'm on, which I'll show you. And the test is just, create a new ERC20X and, do a transfer to the 0 address and assert that it should revert, basically. So just adding a new JavaScript test for Truffle that says transferring to the 0 address should revert. And so now we get the full green on that line saying, hey, you've tested every single opcode associated with that line. And notice we still have the yellows on the arithmetic operators. Those ones we're not going to be able to turn green, so they don't count towards zeroing your coverage. And those yellows are going to be associated with you didn't run a test that causes this opcode to overflow, basically. But you won't be able to write a test that does that in this case. So that's why we don't, by default, count that towards your total coverage score. But it's just a reminder there. It's there for you to remind you, hey, you should think about the cases where arithmetic operators overflow. Okay, so I've shown you how to produce the coverage report. So we went through how to get Firefly set up on your repo. Pretty straightforward. You just have to have Truffle set up and then install the Ubuntu package. And then running it is very similar to running Truffle. You can do it either on your machine or on CI. I've shown you how to navigate this interface here. And one feature that I haven't shown you about this interface is when you create a token, you can control the privacy of the token. So now any reports associated with this token are public, and anyone with the link to the report, like, let me pull it up. Anyone with this link to this report now can view it, basically. Or you can make it private, saying that, okay, only when I am logged in, when my GitHub account is logged in, am I able to view this report. So that's good for controlling the privacy of your code, because we do display in the report your Solidity code. So just be careful of that. You don't want to leak your Solidity code if you're pre-launch or something like that. Okay, now I'm going to start adding some tests. So the first thing you would do to add tests is you would look at your coverage report and you'd say, oh, okay, like, what functionality is not tested yet? So we can just go through here, and it looks like increase allowance is not tested, right? So let's add a test that tests increase allowance. So I'm going to do that locally. Let me share my screen again. I tried yesterday to do the thing where you share an entire monitor, but it crashed my laptop, and now I'm afraid to do it again. So I'm just doing this manual screen share thing. Okay, so I cheated, and I already have the tests that I want to demo written, and so I'm just going to grab them from here. But basically, I'm going to add a test here in the one for the ERC20 that we can increase the allowance of the user. So just give me a second here. Okay. So we've added a test that you can make a new ERC20, and this is not the extended ERC20, it's just the vanilla one. We increase the allowance of account 1 to 10, and then we just check, is the allowance from account 0 to account 1 10, basically. So that's it. I'm going to save that, and now I'm going to just call Firefly test again, and just like Truffle test, I could just do this test ERC20.js. So now I'm just running the tests associated with these arguments are just passed directly through to Truffle, basically. So, and I still have my client running up here in the top, this top window up here, and we can see that our extra test can increase allowance ran. So now I'm going to collect the coverage report again, which is basically just a bunch of queries to the client. You can see that we query a bunch of things to the client to get that coverage report out. And then I'm going to call Firefly upload again. And notice when you call Firefly upload, it returns this report ID, which you can use on CI for immediately having a link to the correct report on your CI infrastructure. So we do offer GitHub integration where we can block PRs from getting merged based on their GitHub status API. So that's kind of the goal of putting that report ID there. So I can just go here to this URL, paste in my new report. And this is the newest report that was just produced. And now look, ERC20 is at 44% coverage instead of the 30% coverage it was at before. And we can go down here, and indeed increase allowance is all green. So we've tested every opcode associated with increase allowance. But if I were to click on this line, for example, and this approved line, which has associated with it an add opcode, you'll notice that the add opcodes are not green, meaning that we haven't tested the overflow case of these add opcodes. That's okay. That's just maybe something you'd want to test, though. So to test that, you would have to call the increase allowance function with an account that already has an allowance. Maybe you set it to like 2 to the 256 minus 3, and then try to increase the allowance by like 7 or something like that. And what that will do is it will cause an overflow in this number right here. In this case, the overflow will go undetected because we're not using safe math. And your test, which will try to assert that the allowance is now the larger number because you're trying to show that the allowance is increased correctly, will fail because actually it will overflow. So the idea behind telling users, hey, you haven't tested the overflow case of this addition operator is to encourage them to write tests that do actually exercise things like overflow and underflow, and that will cause them to have to basically take that into account, to have to see like, oh, could I have an overflow here? And if so, let me write a test that exercises it, and then maybe I should use safe math instead because that test is able to go through, and it shouldn't. So, okay. So that's the first thing you would do when you see a coverage report like this, is you would look for untested methods, you'd look for untested lines like this one, and try to write tests that exercise those lines, basically. So I'm going to do exactly that. I'm going to look for a yellow line now, and I'm going to manually write a test that exercises that yellow line. So I know which yellow line I'm looking for, actually, so I'm just going to go straight to it. Oh, no, it was already this one. I'll just go over the test that I added earlier for it. But this line was yellow before, which basically says that you're transferring to the 0 address. It reverts if you're transferring to the 0 address. Before it was yellow, which meant that we never tested the case where you actually transfer to the 0 address. And so I added a test earlier today that exercises that, which is the one I showed you over here, which is this test. I'll show you it in my terminal here in a second. Yeah, so create the new ERC20, call the transfer function to the 0 address of 10, and it should revert with this error message, transfer to the 0 address. Sorry, my nose is going crazy under this mask. Okay. So let's go back to the terminal and talk about, no, not to the terminal, back to our presentation, and talk about test generation. Or test input generation, I should be more specific. Okay. So I tried to go over as many of the features as I could think of in the existing tool online. Now, next week, we're going to be releasing Firefly version 0.2.0. So we started developing Firefly, just to give a little history, after last TruffleCon, when we were approached by a lot of people saying, hey, it'd be great if you had a tool that was easy for people to use and helped them to improve their quality assurance without having to go to the full formal verification thing. And so that's where Firefly was born, and we've been kind of like working on it and hacking on it as during that time. And we have a lot of features prototyped, and we're kind of trying to pick and choose which features we actually bring to production, but we're very careful about bringing features to production to try to make sure they're well tested first. But for the most part, we've been using the tool internally, actually as a pre-screen on people who approach us for audits and for formal verification, just to see kind of like, okay, where's their quality assurance pipeline at? Are they actually taking the time to write tests and stuff like that? But anyway, Firefly 0.2.0 is due to be released sometime this week. And it adds a new feature that we're calling Blackbox testing, or Blackbox random testing. So we try to generate new test inputs that improve the coverage of your code just kind of without any extra knowledge from you or any extra knowledge about the tests other than what the function signatures of your contracts are. You still have to write what the test should be outputting. You can't just rely on it to generate the outputs for you. But this is actually good because it requires you to think like, oh, okay, here's a test input that exercises a new chunk of my code. What should that test output? And you might find that what you think it should output and what your code actually outputs is different, which in that case, that becomes a bug. So you found a bug. So all it does is generate random transactions that are valid for the contract using the ABI signatures and then sends them to the Firefly client. The Firefly client runs these transactions and measures, did the coverage increase? And then reports back, okay, that this function call increased the coverage, or reports back, didn't find any function calls that increase the coverage. The generation is really naive right now. It's not doing anything fancy. That is something we're planning on changing, but we kind of want to get some just more widespread use of the naive version of it before moving on to improving it from being just a random tester to something closer to a fuzzer. Okay, so I'm going to show you what it looks like to use this. So I'm just going to call Firefly Blackbox. Okay, so we ran the Firefly Blackbox command, and it was targeting this this ERC20 and this ERC20X contract, and by default it will try to improve the coverage of each contract for 30 seconds. So it'll just generate random transactions for 30 seconds, and it'll try to improve the coverage up to 80%. So 80% of the opcodes visited. We found that going beyond 80%, usually you have to have complex branch conditions and stuff like that, so it usually doesn't work out so good. But up to 80%, usually able to get up to 80% coverage. So we starting with testing the ERC20 contract. That's good. The current coverage is at 44 because of that last test I just added. And it found a function call that it was able to make. And of course, these are kind of strange values to be making, but they improve the coverage, so that's good. It also found another function called the symbol function. The symbol function is just a function with no arguments, so all you have to do is call it once in your test suite, and that increases the coverage. Okay, that's good. Also, the decrease allowance. So remember, we added the test manually for increase allowance, but we haven't added any test for decrease allowance. So we add a test for decrease allowance. It improves the coverage by 7%. That's good. And then another call into the transfer function, which started at 72% coverage and goes to 80% coverage. So right now we're not generating like minimized examples of these. They're just kind of random garbage values that are produced. So you could just call it literally with these values, and you'd get the result of this improved coverage. Or you can massage the values a bit yourself to be something a little more sensible, which is what I'm going to be doing. Okay, so ERC20X. Now note we're just providing the test inputs, right? We're just saying like, hey, if you call the transfer function with these arguments, your test coverage improves by 1%, right? So you still have to provide the assertions or the reverts or whatever it is that are expected outputs of these tests, right? So most of these probably, this is greater than the total supply of this gold token that was minted, which is 1,000, right? And so probably this is a revert test. But you have to kind of like think through your own contract logic and figure out, okay, if I call the function like this, what will be the expected output? Okay, allowance function, calling that increased it a decent amount. Calling the name, symbol, and display name functions increased it a bit. Calling increase allowance on the super contract, not the subcontract, increased it. Approve, decrease allowance, total supply, burn-mint. So how I'm going to use this is I'm just going to look at the function names that were called and just write tests for those function names. Now I'm going to cheat again and just use my stash. And wrote a few functions. This is the one that we wrote earlier manually. But here I just wrote some functions of the mint and burn example, right? So we have a new ERC20 ext, and the ext adds the mint and burn functions, recall. Initial total supply of 1,000. And so first I burn some from account 1 of 50, and the new total supply should be 950. And notice that this is a nonsensical scenario, right? Because we're making a new ERC20 where in account 0 there's 1,000 gold and every other account has 0 gold, and now I'm burning from account 1 the 50 gold. And what that should indicate to a user is, hey, you need to be using safe math because this should revert, but it doesn't. And so that we wrote this contract with tons of security holes everywhere just so that we could kind of test things out. And this is one of them. Yeah, so the total supply goes down, but now the balance of the ERC20 ext at account 1 is going to be -50. Well, it's not -50, it's 2 to the 256 minus 50. So somehow something's out of whack there, right? And then the mint function, so we mint to account 1 now 150 tokens. And so it goes from being -50 or 2 to the 256 minus 50 to being 100, basically. And now actually everything is back in order after this call, because we have 1,100 total supply. That makes sense. We went from -50 to 150 on the account 1 there. So that's how we can write a test that exercises the mint and burn functions, but because they're not using safe math, you know, we could just, as we're writing this test, we're thinking, hey, wait, does this actually make sense? No, it doesn't make sense. Why is it that we're able to burn from account 1 even though account 1 has no ether to start, or has no gold to start with? So that's how you could find, oh, okay, I better be using safe math for that burn method. Similarly, we just write a test that that just checks, okay, if we make a new ERC20, do the display name and symbol functions, you know, correctly return their values, which is just to satisfy the coverage collection metric, just to improve the coverage. Another one, are we able to transfer, right? So we start with, on account 0, 1,000 gold, and then we call transfer to account 1, 10 gold, and then we assert that the balances of account 0 and account 1 are adjusted correctly, and we assert that the total supply hasn't changed. That's good. So now we have tests of balance of, and of total supply, and of transfer. And then we also see, can we adjust allowances? So if we make a new one and we increase allowance and we check that the allowance is the increased allowance, but then we decrease it again by 5, so increase it by 10, and we check that the new allowance is 10, and we decrease it by 5, and the new allowance should be 5 now, right? So now we've exercised increase allowance and decrease allowance, and also the allowance getter, the allowance getter. And then also we want to exercise the approve method. So we, make a new ERC20. We approve account 1 to be able to transfer 10 of account 0s. And then we check that the allowance of account 1 for account 0 is 10. And then we approve 5, and we check the allowance is now 5. Right. So these are some tests that are added here. So what I'm going to do is I'm just going to call Firefly test. And we still have our client running in the upper right-hand corner there. Okay, and now there's a lot more tests. There's 13 tests instead of 7 that we started with. And so I'm going to say Firefly coverage -P8145 to collect the coverage information, and Firefly upload. And it gives me this report ID, which if you're using our GitHub status integration would, you could turn into a link and basically just link people to the new coverage report. So let me hop over to my other screen. Here we are. And I'm gonna just jump straight to the report that was generated. And now we can see that our coverage is much better. We're at 83% on the ERC20 and 85% on the ERC20 ext. So we can open it up. and we never tested like the name and symbol functions directly on the ERC20 itself. We only tested on the ERC20X, so that's why it's not showing up green here. There's still a couple of yellow lines here on the transfer. We didn't test the transfer to the 0 address on the ERC20. We only did that on the ERC20X, for example. Same with approve. We didn't approve to or from the 0 address on the ERC20, only on the ERC20X. So let's jump over to that coverage report. ERC20.sol. And we can see, for example, here we did test transfer to the 0 address. We haven't tried minting to the 0 address, which is why this one is yellow. We haven't tried burning from the 0 address, why this one is 0. And so on and so forth. So here's how you can improve your coverage. So I really there was just using the Blackbox tester as a way to know which functions to test more. But in more complicated, and that's because the ERC20 is so simple, but in more complicated scenarios, it'll actually provide you parameters as well, as you saw in the output, that you can feed in and get those tests out that you need for improving your coverage. Okay, and just to recap, during that process, I added these tests of the mint and burn, and specifically the burn, which makes the one balance go negative. That's where the developer has to take the output of the tool, burn this from this address, and realize, hey, wait, I'm able to burn a non-zero amount from an account that has 0. There's something wrong with my code, right? Which is why the Blackbox tester only provides test inputs, because it can't know whether your code wants that overflow to happen or not. Ahead of time, you have to decide that for yourself. So you take the output of it, turn it into tests, and then in those tests, you say, like, is what's happening here sensible, or should it be reverting? And if it should be reverting, then you put in a Truffle assert that it reverts. And if it doesn't revert, then your test will fail, and you have to go back to your code, and you have to say, why did this fail? And you realize, oh, it's because I didn't use a safe math substitution right here. Instead, just use the normal solidity substitution, not substitution, sorry, subtraction right here. So, okay, I'm going to jump back over to the presentation. So once again, that Blackbox feature will be in Firefly 0.2.0, which will be released this coming week. And we'll announce on Twitter when it is released. Okay. Slated for Firefly 0.3.0. So this is an upcoming feature that I'm pretty excited about. We're going to have a property testing library. So not everyone is familiar with property testing. Property testing is basically the ability to write a test that states the intended behavior over a large chunk of inputs rather than over just some concrete specific input. So if you've used something like quick check in Haskell, or you used hypothesis in Python, these are property testing frameworks. They let you specify properties of your code, and then what they do is for some variable that's in your test, they fill in a random value and run the test on that random value, and then check, did the test pass on that random value? Maybe they do this a few thousand times. So you can really quickly test a huge chunk of your input space without having to write that much more complicated of a test. Now, the benefit of using our K and KVM is that we can not only do it with random values, we can do it with fully symbolic values. So this is where we can slowly turn the dial up from just testing to property testing to actual formal verification, to lightweight formal verification that you can do before even approaching us to do full formal verification of the entire thing. So here's an example of a property test that I've put here on the slide, just so I could walk through it as an example. So first, we ship with a smart contract that we call symbolic test built-ins. That name is going to change once this tool goes live to something like Firefly check or Firefly hypothesis. I don't know. We'll have to decide on the name. We create an account in ERC21, and then we tell the testing harness, okay, set the account storage to an arbitrary, fully symbolic storage. So we just say, like, what if it was any pre-state? We say we get a new address called from, that's just the address of this contract. a new address called 2, we generate some new symbolic address. That's going to be an unconstrained symbolic address that just can be anything. And some value that we're going to transfer, which is also some unconstrained new uint 256. So in the case of random testing, what these functions here, these new symbolic address, new symbolic uint 256, they will evaluate to random values that are in the appropriate range. So a new symbolic address will be between 0 and 2 to the 160, and new symbolic uint 256 will be between 0 and 2 to the 256. But here I'm showing you an example of symbolic. So actually they're just going to be fully logical symbolic variables instead, and we're going to be doing symbolic execution with them instead. Then we balance the from address as token.balance of from. Now remember, from is the address of this, but the storage is completely symbolic. So that balance is going to be just completely arbitrary. There's going to be no constraints on it other than the fact that it's associated with the address of the address of this, right? So address this. So now the balance from is some arbitrary balance that's coming, that all we know is, hey, it's the correct balance from. And then we require that the value that we're transferring is greater than balance from, basically. So the amount that we're trying to transfer is more than it should be. But otherwise, these are unconstrained values. Value and balance from are totally unconstrained. And then we try to do the transfer, so token.transfer to and value. And we store, did this transfer work, basically. And then we assert at the end, no, the transfer should not work. So assert not success in this case. So this is a test where we didn't fill in a single concrete value. We didn't fill in anything that said, you know, the balance from is 300 and the value we're trying to transfer is 350 or something like that. We just let them be fully symbolic, fully arbitrary, and we symbolically execute it, and we check, you know, every time that the value you're trying to transfer is greater than balance from, does it correctly not succeed in the end, basically. So we have a bunch of these tests written for ERC20 specifically, and we're working on generalizing the tool for broader use, and so that you can write your own tests. And we're really trying to focus on making it so that the language you write the tests in is as familiar to you as possible. So that's why we're doing it using this extra symbolic test built-ins contract, which kind of gives you the levers you need to be able to write these tests yourself. Okay, so that's an upcoming feature. I'm pretty excited about that feature. I'm hoping people will use it because if you just write a few symbolic property tests for your contract and you run it through the tool and the tool says yeah, then you've done formal verification at that point. You know, you have formally verified that this property holds for your contract. And it's as easy as writing another solidity test, which, you know, if you're a solidity dev, it's already familiar to you. It's just you have to get familiar with this concept of, you know, generating new symbolic variables and then constraining them using requires clauses, as opposed to putting like address 2 is equal to some hard-coded address or something like that. So that's the new extension you have to get used to. But once you're used to that, you can write down property tests and actually do your own lightweight formal verification. Okay. So one last thing I want to go over is we do have an alpha ERC20 tool, verification tool available now. It is based on this symbolic property testing. Like I said, this is very alpha, use at your own risk type of thing. But you can go here and it opened in the different windows. So let me do that. Let me just go over this slide first and then I'll switch over to that. It's a special case of the Firefly property tests that I just went over. And we just basically have a suite of symbolic tests for ERC20s that we run on your contract and report back, you know, this test succeeded, these tests failed, yada, 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 right? We envision this being useful for developers who are writing contracts that need to interact with external tokens. So this would be like swap contracts or DEX contracts or stable coins that accept collateral that are ERC20s, these types of contracts. So then you can vet your external ERC20 and make sure it will actually behave like a proper ERC20 rather than some other contract, basically. So Like I said, this is very, very alpha. Don't expect it to work if you try it, but we do need it battle tested. So if you're willing to put up with things not working, using the tool is really easy. It's just that don't expect it to work, right? We're still in the process of proofing it, basically. Let me show you the website. This is the, I'll give it a second. There we go. This is the website. Pretty simple website. Right now we're thinking, okay, you just submit your etherscan.io contract address, and then we'll pull all the information we need from there. Or if it's not deployed, submit your constructor bytecode, which you can get out of the Solidity compiler, and you can either drop that file here, or you can submit it here. And ideally, you'd also supply the Solidity code needed for that. We don't really need it, but it makes the error messages we produce more meaningful. And then you give an email address, because this is not an instantaneous tool. It takes time, usually a few days at least. And we'll send you back a report with a link to your report. The report will look something like this. For failure cases, for success cases, it'll just say succeeded. But for failure cases, it'll say, here's the symbolic test that we ran. It failed on this assert, so it failed on kassert 0. So for some reason, this ERC20 that was submitted was not returning false when it should have been on this transfer. And then we'll include some output of the K tool, which may be a little esoteric, but you can just email us to get a better idea of what it's saying, basically. We try to provide a little bit of information here, but you really have to know K to be able to read this output. So really better just email us and be like, hey, what is this saying? What does this mean about my contract? And then we can open a dialogue there with you. So back to the website. I feel obligated to show you this disclaimer, so make sure you read that disclaimer. And like I said, this is an alpha tool, so use it. If you're using it, it's for our benefit to be able to test our tool, basically. It's not something that you should use live or for production at this moment. But we would sure appreciate it if you did go and try and use it, and then we can improve the tool to the point where we feel comfortable saying, like, okay, you can use it for something that's going live.